2,200,000,000 tons of waste are generated across the entire globe every single year. Why does paper represent nearly 26% of this staggering total, making it the most frequently discarded material on the planet? At first glance, the sheer volume of paper thrown away seems manageable, but in reality, it could cover millions of football fields annually. The recycling process allows this material to be reused up to 7 times before the fibers finally become unusable. Hundreds of tons of discarded paper arrive daily at one of the largest specialized recycling facilities in the United States to begin a mechanical transformation. The camera glides along the massive intake bays where compressed bales of waste are stacked 3 stories high. One can notice how hydraulic manipulators systematically move these dense blocks toward the primary conveyors. It gets more complex further on. Equipment gradually breaks down the compacted masses into individual sheets and fragments. The process is only gaining momentum as the material is prepared for its chemical and physical rebirth. One can notice how the conveyor belts move at a steady speed of 2 meters per second, feeding the intake hoppers without interruption. Everything only gets more complicated as the dry waste transitions into a liquid state. The facility operates continuously to ensure that every scrap of old paper is converted into bright white rolls of toilet paper. High-pressure water jets and mechanical agitators work in unison to separate the ink from the cellulose. The fibers are refined and smoothed through a series of automated screens and filters. This ensures the final product meets the exact standards required for daily domestic use. The material leaves the primary processing zone, transitioning into a calm stage of drying and winding. 500 tons of waste on average arrive at the sorting facility every single day to undergo a rigorous separation process. Why is such a massive volume of discarded material collected with such precise timing and coordination? The transformation from a pile of refuse into a valuable industrial resource would be impossible if the initial sorting were not handled with extreme mechanical accuracy. Modern recycling technology ensures that paper, which seemingly lost all its value, including old newspapers, discarded cardboard boxes, and various invoices, can be granted a second life. But this is just the beginning. The journey starts at the curb of local neighborhoods. Recycling trucks navigate through residential streets as part of their daily rounds to gather raw materials. One can notice how hydraulic mechanical arms extend with a measured hiss to lift the bins and deposit every fragment of used paper into the rear compartment of the vehicle. The trucks operate with a smooth, rhythmic efficiency that minimizes delays during collection. It gets more complex further on. The convoy of vehicles maneuvers toward a specialized plant that serves as the central hub for waste management in the surrounding communities. At first glance, the piles of mixed refuse appear chaotic, but in reality, they are the foundation of a sophisticated industrial cycle. Automated systems and manual oversight work in tandem to isolate paper from a mixture containing metal, glass, and various plastics. The equipment gradually separates the fibers from non-recyclable contaminants. It is visible how the sorted paper is organized into distinct categories to ensure the quality of the final product remains high. The process is only gaining momentum. This careful isolation allows for the production of fresh, bright white rolls that serve essential daily purposes without requiring the felling of forest timber. The materials undergo thorough cleaning and processing to remove inks and adhesives. This ensures the output is soft and meets strict hygiene standards before it reaches its final destination in domestic settings. One can observe the heavy machinery compressing the cleaned pulp into massive industrial cylinders. From here, the transformation moves to the next phase of processing as the material is prepared for its final shaping. 100 rolls of toilet paper are consumed by a single person every 12 months on average. This staggering volume of waste begins its transformation in a state that is rarely clean or uniform. Recycled paper arrives at the facility saturated with a vast array of impurities, ranging from resilient nylon fibers and fragments of hard plastic to small metal scraps and organic food residues. The entire unsorted mass is deposited onto an expansive conveyor belt that transports the mixed waste toward the primary sorting zone. Why is human intervention necessary at the very beginning of the belt? It seems that mechanical systems should handle the load immediately, but manual sorting remains a critical safeguard, as workers must quickly identify and extract large pieces of nylon and other disruptive materials that could jam downstream machinery. Only newspapers and printed sheets that maintain a specific level of cleanliness are permitted to remain on the line. The workers perform their duties in constant, direct contact with the waste materials throughout their entire shifts. One can notice how they are equipped with comprehensive protective gear, including thick rubber gloves, filtration face masks, and impact-resistant safety goggles. This manual stage ensures that the most obvious contaminants are neutralized before the process gains momentum. It gets more complex further on. After the initial manual extraction, the paper stream enters a vibrating material separator, which serves as a fundamental mechanical filter for the mixed input. The equipment gradually spreads the paper across a broad, oscillating metal surface. One can notice how the mechanical vibrations cause the lighter paper sheets to migrate toward the front of the machine. Simultaneously, heavier objects such as dense cardboard, plastic fragments, or metal bits lose their footing and fall through specialized gaps below. Everything only gets more complicated as the paper reaches the air separator. This specialized device utilizes a combination of high-velocity wind currents and sophisticated optical sensors to execute the final stage of purification. As the material passes through the sensor field, the system automatically detects lightweight non-paper objects like plastic film, wrappers, and soft packaging. In a fraction of a second, high-pressure air jets detonate with a targeted burst, blowing the unwanted debris off the line while the paper continues its trajectory. At first glance, this level of sorting seems sufficient, but in reality, modern facilities are pushing toward total automation. Some plants now utilize advanced robotic arms integrated with computer vision systems. These manipulators identify waste types based on precise geometry, material density, and color profiles. The robotic grips move with jewelry-like precision, placing items into designated bins at speeds far exceeding human capability. This transition to the next level significantly reduces the reliance on manual labor while increasing the purity of the final output. The refined paper is eventually funneled into a heavy-duty industrial shredder. Inside the housing, sets of hardened metal blades rotate ceaselessly, tearing every sheet and fragment into uniform thin strips. The shredded material accumulates in massive heaps on the facility floor, where the dust slowly settles between cycles. But this is not the limit of the processing chain. A massive industrial bulldozer maneuvers across the concrete floor to engage the shredded piles. The machine pushes the loose paper into a high-pressure pressing chamber with a steady hydraulic force. Inside, the strips are compacted under immense weight until they form dense rectangular blocks that resemble giant recycled bricks. The process concludes this phase as a forklift slides its tines under the finished bales. The equipment lifts the heavy blocks with a rhythmic hiss of hydraulics and loads them into waiting trucks. These transport vehicles depart the facility, carrying the raw material toward the specialized factory where the paper will be pulped and reformed. Thus, the sorted waste reaches the standard ready for the further stage of production. 800 kilograms is the exact weight of a single compressed bale of shredded paper as it arrives at the industrial processing facility. Why is such a massive volume of waste material transported with such urgency to the factory gates? A single one of these dense blocks contains enough raw cellulose to manufacture more than 10,000 individual rolls of finished product. This efficiency transforms discarded remnants into a vital household commodity through a sequence of high-precision mechanical stages. At first glance, the arrival of raw material seems like a simple logistical task, but in reality, it is the start of a complex chemical and physical metamorphosis. Forklifts maneuver with calculated movements to deposit the bales into the receiving zone, where the industrial feeding process commences. The shredded material is immediately funneled into a pulper, a massive stainless steel tank designed for the primary breakdown of solids. Inside these vessels, the paper is submerged in water at a strictly maintained ratio of 1 part solid material to 10 parts liquid. It is visible how the mixture begins to churn as the breakdown starts. Everything only gets more complicated as the mechanical forces take over. 1,500 revolutions per minute is the maximum speed reached by the high-powered agitator located at the very base of the tank. This rotation creates a violent, swirling vortex that forces the water through the paper fragments to isolate every individual cellulose fiber. Depending on the specific engineering of the system, a single batch can process anywhere from 2 tons to 10 tons of paper. The camera glides along the surface where the turbulence ensures the creation of a fine and uniform slurry. This stage is the fundamental requirement for the hygiene and consistency of the final sheet. Specialized chemical agents are introduced into the swirling mass to perform deep purification of the fibers. These additives include dispersing agents and de-inking compounds that target the molecular bonds of printing inks, adhesives, and synthetic surface coatings. As the agitator continues its ceaseless rotation, the slurry becomes progressively more refined and free of contaminants. One can notice how the dark remnants of ink are separated from the whitening mass of pulp. The process is only gaining momentum. Natural hydrogen links begin to form between the fully separated cellulose fibers as they start to intertwine within the liquid medium. This automatic bonding process establishes the primary structural integrity of what will eventually become a solid sheet. The mixture transitions from a chaotic, dispersed state into a predictable, uniform suspension. This transformation typically requires a duration of 30 to 60 minutes of continuous processing. The exact timing is determined by the specific grade of the raw material and the intended thickness of the paper. 95% of the resulting mixture consists of water even after the initial pulping phase is complete. Why must the facility move such a high volume of liquid through the machinery? The water serves as a carrier for the fibers, but it must be systematically removed to build the necessary thickness and strength of the material. The slurry is therefore pumped into a dewatering system equipped with massive rotary drum machines. Metal cylinders spin without interruption, causing the saturated pulp to adhere to a fine mesh screen as it rotates. Excess water is forced through the mesh and captured by a recovery system positioned directly beneath the spinning drums. This creates a moist and inflexible layer of concentrated pulp that is ready for the next phase of mechanical compression. One can notice the transition from a liquid stream to a damp, solid mat of fiber. The material is now prepared to enter the pressing and shaping station. But this is just the beginning. High pressure is applied as the damp pulp is fed between large steel rollers covered in a specialized fine mesh. These rollers rotate in opposite directions, performing the dual task of defining the width of the sheet and extracting residual moisture. The constant pressure flattens the material until it reaches a standard thickness of 15 to 20 microns per layer. The equipment gradually compresses the fibers to ensure the sheet is consistent across its entire surface. It gets more complex further on. Mechanical strength is granted to the paper during these few seconds of intense compression and rapid movement. The pulp is now a continuous uncut sheet of paper that possesses the durability required for consumer use. After the initial formation, the material passes through a calendaring system where the surface is polished and smoothed. The camera glides along the high-speed line as the paper takes on a subtle shine. This ensures that the final product meets the tactile standards expected by the end user. 1 meter in diameter is the minimum size of the massive reels that collect the continuous paper at the end of the drying line. Each of these industrial reels holds several thousand meters of material wound tightly around a central spindle. Once the capacity is reached, specialized lifting equipment lowers the reel from the machine for transport. A forklift then moves the bulk paper to the cutting line for final processing. The paper component is now complete, but the structural core is still missing. Recycled cardboard is used to manufacture the rigid tubes that occupy the center of every roll. These strips of cardboard are fed into a spiral winding machine that wraps them around a solid steel rod. A specialized industrial adhesive is applied during the winding process to ensure the hollow tubes can withstand the pressure of high-speed paper winding. One can notice how the layers overlap in a precise geometric pattern. The process is only gaining momentum. 9 to 11 centimeters is the standard length of the segments cut from the long cardboard tubes. A rotating blade slices through the hardened cardboard with millisecond precision, creating uniform cylinders with a diameter of 4 centimeters. These dimensions are critical for ensuring the cores fit perfectly onto the winding molds of the next machine. Precise cutting prevents any risk of jamming or misalignment when the paper is applied. The tubes are now ready to be integrated into the final assembly. 3,000 revolutions per minute is the speed at which the winding shaft rotates during the final assembly stage. The hollow cardboard cores are placed onto the shaft, and the wide paper sheets are sliced and wound onto them simultaneously. This high-speed rotation ensures that every layer of paper is stacked with perfect alignment. Once the pre-programmed length is achieved, The system severs the paper and applies a light adhesive to secure the outer tail. The finished long rolls are then deposited onto a conveyor belt. Dozens of uniform white cylinders line up in perfect order as they move toward the intermediate storage area. It seems like a simple holding stage, but in reality, this section regulates the production flow between the winding and packaging departments. Stepped ramp conveyors allow the rolls to move into designated positions without human intervention. Advanced sensors monitor the volume to prevent bottlenecks in the production chain. Everything only gets more complicated. Thousands of revolutions per minute are maintained by the ultra-sharp blades of the final cutting machine. The long rolls are sliced into individual units with exact dimensions, guided by precision compression systems that prevent any tearing of the edges. One can notice how the blades move through the paper with jewelry-like precision. After the cut, the small rolls move as perfectly round blocks along a high-speed belt. This format is designed to allow for smooth unrolling during later use. Transparent plastic film is unrolled from large spools as the rolls enter the automated packaging zone. The machines wrap the film around packs of 6 rolls with millimeter-level accuracy before sending them to the heat-sealing station. Controlled thermal energy melts the edges of the plastic to create a durable, airtight seal. This barrier protects the paper from moisture, dust, and bacterial contamination during its time in the warehouse. The packaging process concludes with the final transition to the shipping area. Robotic arms equipped with intelligent control systems perform the final task of palletizing the finished goods. These manipulators pick up the sealed packs and stack them in a pre-programmed pattern that maximizes the stability and space of the pallet. Sensors ensure that every layer is perfectly aligned before the load is moved to the distribution center. Thus, the material reaches the standard ready for the further stage of delivery to supermarkets. The production cycle is now complete, transforming waste paper into a finished hygienic product. 80 billion rolls is the staggering total volume of toilet paper consumed across the globe every single year. Why is such a seemingly simple and mundane household item responsible for such massive industrial output? At first glance, a single roll appears insignificant, but in reality, its production represents the final stage of a complex mechanical and chemical journey that originates deep within natural ecosystems. 100 rolls of paper are used by a single person on average throughout a one-year period. This individual consumption pattern drives a global manufacturing cycle that never stops. The process is only gaining momentum. One can notice how massive tree trunks are harvested from vast forests to serve as the primary raw material. Despite the evolution of materials, the core of this product remains wood fiber. The industrial sequence involves stripping the bark and grinding the timber into a soft, malleable pulp through high-pressure mechanical or chemical processing. But this is just the beginning. 15 million hectares of forest are consumed by the global paper industry annually to sustain this level of production. This area of lost woodland is equivalent to nearly 1/5 of the entire Amazon rainforest, which functions as the primary green lung of the planet. It is visible how the scale of extraction impacts the environment as these towering ecosystems are converted into short-lived, single-use commodities. Everything only gets more complicated when considering the sheer speed of disposal. The equipment gradually transforms the raw pulp into incredibly thin sheets that must maintain a specific tensile strength. It only looks obvious that the paper should be soft, but in reality, achieving the necessary balance of comfort and durability requires precise calibration of the rolling machinery. The sheets are layered and wound onto cardboard cores at high speeds, creating the familiar cylindrical form found in every household. Fortunately, the industry has begun to identify alternative pathways for sourcing materials. Transition to the next level. These new methods aim to significantly reduce the ecological footprint of the manufacturing process without requiring a sacrifice in the final quality of the product. The search for more sustainable fibers is now a primary focus for engineers and environmental scientists alike. The molten-like slurry of wood fibers moves through the final drying sections of the production line. This concludes the current phase of the manufacturing cycle, paving the way for more sustainable innovations in the future. 100% of the discarded paper fibers have completed their transformation from what at first glance seemed like worthless waste into a functional essential. Why is this transition from raw scrap to a refined finished product so significant? The complexity of the reclamation process often remains hidden behind the simplicity of the final item, but the chemical and mechanical journey ensures that no fiber is lost. Every stage, from the initial sorting to the final winding of the rolls, is calculated to maximize the utility of the reclaimed material. This technical cycle does not end with mere collection. It only gets more complicated as the material moves through high-speed shredders and industrial pulping tanks where impurities are purged. One can notice how the dark grayish slurry gradually lightens as the automated systems filter out inks and adhesives, leaving only the pure cellulose behind. The equipment gradually presses the pulp into vast thin sheets that move across heated cylinders at high velocities. This is just the beginning of the finishing phase. The camera glides along the massive rollers where the paper acquires its final texture through embossing and perforation. It only looks obvious that a roll of paper is a simple object, but in reality, it is the result of thousands of individual fibers being restructured under precise pressure. The transformation from bulk material to soft white toilet paper rolls, found in nearly every household, is now complete. Everything only gets more efficient as the technology for recycling continues to evolve and stabilize. Thus, the steel-like precision of the recycling machines concludes this phase, and the material is ready to move to the next processing phase without haste. The cycle of rebirth for the paper fiber reaches its logical end, proving that even discarded scraps have a place in the industrial chain. From here, the finished rolls are packaged and prepared for distribution, closing the loop of production.